Welcome to Elementary Real Analysis. Today, we are going to explore a fascinating topic called alternating series. If you have ever wondered how mathematicians and computers can add up an infinite string of numbers without everything blowing up to infinity, you are in the right place. We will build this from the ground up, so do not worry if it sounds intimidating right now. Let us dive in and discover the hidden balance within infinite sums. To understand what an alternating series is, imagine you're following a confusing treasure map. You walk 1 meter forward, then half a meter backward, then a third of a meter forward, and so on. Because you keep switching directions, you are alternating between moving forward and backward. Since your steps are getting smaller, you eventually settle down at one exact spot. In mathematics, this is exactly how an alternating series behaves. Instead of just adding numbers forever and blowing up to infinity, we add, then subtract, then add, then subtract. This constant push and pull makes it much easier for the total sum to settle down or converge to a single finite number. Now that we understand the idea of moving back and forth, let us look at how we write this mathematically. This formula is the standard representation of an alternating series. The large summation symbol tells us we are adding an infinite number of terms. The variable a sub n represents the absolute size of each step, which is always positive. The magic happens with the negative 1 raised to the power of n plus 1. This acts exactly like a light switch. When the index is odd, it is positive, and when even, it is negative. If you increase the index, you generate the exact back and forth pattern of addition and subtraction you see on the right. This formula we just saw leads us to an important question. How do we know if this back and forth series actually settles down to a single number? To answer this, we use a famous mathematical rule called the alternating series test, widely known as the Leibniz test. The Leibniz test states that an alternating series will definitively converge, meaning it will settle on a finite number if it meets two simple conditions. First, the absolute size of the steps must be constantly shrinking. Second, the size of those steps must eventually shrink all the way down to exactly zero as we go to infinity. If both are true, convergence is guaranteed. Let us translate those two rules into formal mathematics. Here, we see the two exact conditions of the Leibniz test. The first part of the formula, a sub n plus 1 is less than or equal to a sub n, represents the requirement that the sequence of positive terms must be decreasing. The inequality ensures every new step we take is smaller than the step before it. The second part uses limit notation to ask what happens as our index grows infinitely large. It strictly demands that the ultimate size of the terms must be exactly zero. If the terms shrink but stop at a number like 1/2, the series will never settle down. Before we move on to proving why this works, let us see this with a concrete example. We will look at a classic problem, determining if the alternating harmonic series converges. We are given the series with terms alternating in sign divided by n. Our strategy is to break the series down into its positive components. We strip away the alternating sign multiplier to isolate the positive sequence a sub n, which is simply 1 divided by n. To check our first condition, we find the next consecutive term by replacing n with n plus 1. Because the denominator of the new term is larger, the overall fraction is strictly smaller, satisfying our first condition. Continuing with our example, we must now check the ultimate destination of these terms as the index grows infinitely large. We set up the limit of 1 divided by n as n approaches infinity. As the denominator grows toward infinity, the value of 1 divided by that massive number shrinks down to nothing. The limit evaluates exactly to 0. This perfectly satisfies the second and final condition of our test. Because the terms are strictly decreasing and their ultimate limit is 0, the alternating harmonic series converges. Physically, this means the back and forth cancellation creates a perfect balance, allowing the sum to settle on a finite, exact number. Now, let us examine a scenario where an alternating series might fail to converge. We are given a series where the numerator and denominator grow at similar rates. Our strategy remains exactly the same. We first extract the positive portion of the series, ignoring the sign flipping mechanism, giving us n divided by n plus 1. We will jump straight to testing the second condition, paying special attention to the limit as the index approaches infinity. To evaluate this limit properly, we use a standard algebraic trick, dividing both the numerator and the denominator by the highest power of the index present, which is just n itself. Continuing our calculation, we look at what happens as the index goes to infinity. The small fractional part, 1 divided by n, shrinks to exactly 0. The rest of the expression simplifies easily, and the final limit evaluates to the number 1, not 0. This is a critical failure of our required conditions. Because the limit of the positive terms is 1 and not 0, the series completely fails the Leibniz test. Physically, this means the individual steps never vanish. Instead of settling down, the running total will just bounce back and forth endlessly between two different values, meaning the series diverges. Now that we have successfully used this test, let us understand where it comes from by proving it. We will look at the partial sums, which are simply the running totals as we add the series term by term. We start by looking at what happens when we add up an even number of terms, calling this S sub 2m. We group the terms into pairs. Because our first rule stated that the terms are always decreasing, the first number in every parenthesis is larger than the second number. Therefore, every single grouped pair results in a positive number. This proves that as we add more pairs, the running total for even terms is strictly increasing. Continuing our proof, we take the exact same running total but group the numbers differently. We start with the very first term and then subtract a series of grouped pairs. Just like before, every grouped pair inside the parentheses is a positive number. Because we are starting with the first term and only subtracting positive amounts from it, this proves that the even running total can never be larger than the very first term. We have just proven that the even running totals are always growing but are trapped beneath a solid ceiling. The monotone convergence theorem guarantees that this sequence must eventually settle down to a specific limit, which we will call S. For the final step of our proof, we must figure out what happens to the odd running totals. We find an odd running total by taking the previous even running total and simply adding the very next term. We then apply a limit to both sides as the number of terms grows to infinity. The even running total turns into our settled limit value S. At the exact same time, our second rule of the Leibniz test guarantees that the single extra term shrinks to exactly 0. Adding 0 changes nothing, so the odd running totals settle down to the exact same limit S. Since both zero in on the same number, the entire series converges. This diagram perfectly visualizes the proof we just completed. Look at the number line and follow the arrows. You can see the running totals jumping back and forth. We start at 0, take a large step to the right to reach S1. Then a slightly smaller step back to the left to reach S2. Because the jumps get strictly smaller and smaller, the totals are forced to spiral inward. They can never escape the bounds created by the previous steps. Eventually, this back and forth motion locks onto the final limit value in the center, labeled S. This is the physical meaning of an alternating series converging. Now that we have proven how this works, let us look at why it matters in the real world. Alternating series are incredibly important in fields like numerical analysis and computer science. When your calculator computes complex trigonometric functions like sine or cosine, it does not draw a physical triangle. Instead, it adds up an alternating series called a Taylor series. Because the terms alternate back and forth, engineers can easily calculate the maximum possible mistake. The Leibniz test guarantees that if you stop adding terms at any point, your total error is strictly less than the size of the very next term you ignored, allowing computers to guarantee highly precise answers. Let us summarize the most important ideas we have covered today. An alternating series is a sum of numbers that strictly switches between positive and negative values. To determine if it settles on a finite number, we use the Leibniz test, which provides a simple two-step checklist. The terms must steadily decrease in absolute size, and their ultimate limit must be exactly zero. This back-and-forth cancellation makes alternating series much more likely to converge than series with only positive terms. You now understand both the mechanics and the proofs behind alternating series. Excellent work today.